So we want to look at, for homework, 1611, which begins on the bottom of page 367 of the Whit and Whit book and goes to the top of page 368, and the top of 368 is where the data is presented. And what we're doing, we're counting driver errors according to how much alcohol was being consumed. No, you cannot volunteer for this study. It's already been done. So we have a number of people who are given no alcohol, and we record their errors, and then 1 ounces, 2 ounces, 4 ounces, and 6 ounces respectively. So to put this in SPSS, and again, the intent is for it to be done in SPSS. So we're going to open up an SPSS document, and we're going to go to variable view where we name the variable. What are our two variables? What are all the numbers in the body of the table? No, those are the amount of alcohol is those are the column headings, and that is the other variable. So I'll just say amount of alcohol. I'll just say it that way. And the other is the number of driving errors. So I'm going to say driving errors. And keep in mind you can't put spaces in here; it'll yell at you. So I'm going to put those two under variable view. No, it's not showing up on the whiteboard. That's just in the, yeah, let me share the SPSS there. I did not set that to come up. Good thing I hadn't put anything in there just yet. Okay. If I can make that a little bigger here. There it is. Okay, thank you. So, again, notice I'm on variable view. The lower left, the second button is clicked, and so we're naming and defining our variables. Just call it one variable amount of alcohol, the other driving errors. So when we go to data view, these two variables will become column headings, and there they are. So the amount of, and notice what I can do with this. The amount of alcohol is given to us numerically, 0, 1, 2, 4, 6. I can use those numbers for the amount of alcohol. So I have 1, 2, 3, 4. I have 5 persons under each amount of alcohol. So I'm going to have 5 people who consume no alcohol. I have 5 people who consume 1 ounce of alcohol. And the order's not, you could do the driving errors first. Have 5 people who consume 2 ounces of alcohol. 5 people who consume 4 ounces of alcohol. So again, notice even though it's skipping things, I can put in the exact numbers they're giving us because they're just looking for numbers. And then 5 people who consume 6 ounces of alcohol. So to fill those in specifically, the people who consumed 0 alcohol made these number of driving errors respectively: 1, 1, 3, 6, 4. Double check, make sure I'm putting those in right. All the driving errors are going in the same column, even though they're not in the same column as they're presented to you. But they're measuring the same thing. So if they're measuring the same thing, that's the same variable. So the number of driving errors made by drivers who consume 1 ounce of alcohol would be respectively 4, 3, 1, 7, 5. Those consuming 2 ounces of alcohol made these driving errors: 6, 1, 2, 10, and 7. If they consumed 4 ounces of alcohol, they made either 15, 6, 9, 17, or 9 driving errors. And finally, the errors made by those consuming 6 ounces were 20, 25, 10, 10, and 9. Again, and make sure you go past that last cell. You don't just leave the cursor on there. So we've got our data entered. The question is, Does there seem to be any kind of difference in number of driving errors according to how much alcohol is consumed? I have 1, 2, 3, 4, 5 groups. And by the way, some of you are brave enough to write this up for your data analysis assignment, so you get an extra, some difficulty points for that because of 5 groups, you got a lot of pairs to double check. As we're going to see in just a minute. So we're ready to analyze. We're going to go to General Linear Model. Again, keep in mind there is an Anova option under another menu here, but we're going to go to this because when we get into stuff later, next course, this will always work to go this way. So it's going to be univariate, and we'll talk more about what univariate and multivariate mean also. I already mentioned it in terms of the number of dependent variables. So our dependent variable is driving errors. Our fixed factor, and again, fixed factor is, in this case, synonymous with independent variable. That's the amount of alcohol consumed. I don't think we want anything in model. Again, that's another procedure. Post hoc. Again, our groups are amount of alcohol, and we're going to look at the Tukey follow-up test. And do we want anything under options? Yeah, I want some information under options. I want the descriptive statistics. I want effect size. I'm not going to worry about some of this other stuff right now, but this is going to be conducted at the, did we decide this is the 0.05 level of significance? Doesn't say, so therefore it is. Let me mention another thing here. The 2 ways we have of effect size, the Cohen's d and the eta squared, just think of them interchangeably. If it asks for one, it's okay. Just give the other. Whichever one, obviously whichever one SPSS spits out the easy one. Go the easy route. So when I ask for effect size, that's going to give me eta squared, although I think that's the one they asked for in the text here anyway. So I think we're ready to continue with this. I don't think we want any other options, so we're going to click OK and get an output window. And our output window gives us a big mess. Let's see if I can make this a little larger so we can see as much of it as fairly possible. I don't want to lose anybody on the board, though. Okay. I have means and standard deviations for each of my 5 groups. No alcohol, 1 ounce, 2 ounces, 4 ounces, and 6 ounces. And the question is there any significant difference between any of these means with any other means? And I find out down here, under my test of between subject effects, the key things are under degrees of freedom. Remember, we're looking at, in this case, 4 and 20. Why 4? Where does 4 come from? Besides it spits it out, why does it spit out 4? Okay, because there are 5 groups. 5 minus 1 is 4. And why 20? 4, and this is the between groups. Where does the 20 come from? It'd be the number altogether, 25 minus 5, because there are 5 groups, that's 20. Or there would be 4 degrees of freedom in each of 5 groups, which is still 20. I'm also concerned with the F value, which is 6.737. The significance, which is the p-value, which is 0.00, which answers the first part of our question right there, and our eta squared, which is 0.574. So at some point, we're going to say, and again, this is an F value, an F of 4 and 20 degrees of freedom, respectively. That value is 6.737. The p-value is equal to 0.001, and because that's less than 0.05, that's significant. And then our eta squared is going to be 0.574, which I believe I think that's a large effect size. Okay, so keep in mind that an analysis of variance has either 1 or 2 steps. And we already know this one's 2 steps because our p-value is significant. The p-value is less than 5. And again, let me say this again. Universally, we've never contradicted this, and I don't think we're, well, we're not going to overall, but we're going to make some adjustments later. If P is less than 0.05, there is significance, a significant difference or significant correlation or something significant. In this case, we're looking for significant difference. Anytime P is less than 0.05, that says something. This is like my illustration. Last time we talked about this, I said it's kind of like if you're asking someone, do you know what time it is? And if the answer is yes, there's a follow-up question. So in this case, because P is less than 0.05, yes, I know what time it is. Okay, follow-up question is, well, what time is it? In this case, the follow-up question is, oh, is there significance somewhere? The answer is yes. Okay, the follow-up question is, okay, where? And I have to scroll down. I will lose my ink layer when I do this, but that's okay. I have to scroll down to, so again, this is the first paragraph. Multiple comparisons. I said there's 5. Look at all this mess. But again, remember, there's duplicate information here. We want to compare everything with everything else, but we only have to do that in one direction. So I'm going to compare and look at the pattern. And I mentioned there's a pattern to this. We did examples with 3 groups. And so this is the one with 5 groups, but we're going to see a similar pattern. Okay, I'm going to compare the no alcohol with 1 ounce. Oops. So none with 1, none with 2, none with 4, none with 6. That compares the no alcohol to every other group. I'm going to compare 1 ounce of alcohol with. I don't need to compare with no ounces because I already got that. So I'm going to skip that first one. I'm going to compare 1 with 2, 1 with 4, 1 with 6. Now I'm going to compare 2 with everything else. I don't need to compare 2 with 0 or 2 with 1. I've already got those. So skip the first 2. See the pattern? So 2 with 4 and 2 with 6. To compare 4, the only thing I haven't compared 4 with is with 6. So skip the first 3. And then there's nothing in that very last section I need to compare 6 with. I've already got 6 compared with everything else. So for the lines I'm talking about, or the comparison I'm talking about, which would be, and I'll just mark off the lines that are pertinent here, all these, not the first one here, not the first or second one here, not the first, second, or third one here. So those are the ones that I want to compare with. And the key thing is what is this number in this column? And the question is, where is it less than 0.05? Not here, not here, not here, but close. Here, not here, not here, not here, here, not here, here, not here. So what this means is if I compare 0 with 1, I don't get a significance. 0 with 2, I don't get a significance. 0 with 4, I don't get a significance, but this is the kind of high stakes thing to where, oh, there's not really, there's a 5.5% chance there's not really a difference. Well, that when you're talking about drinking and driving, this is one of those cases I'm not sure I'd go strictly. I might would go with the 0.1 or maybe even higher than that in this case. But to go with the 0.05, when you compare 1 drink with 6 drinks, there's clearly a significant difference. When you compare 2 drinks with 6 drinks, there's clearly a significant difference. I'm sorry, 0 with 6, 1 with 6, and 2 with 6. And really, when you start comparing 2 with 4, it's not significant, but it's less than 0.5. That means there's probably, not 0.5, but 0.5. So what this would seem to suggest is you start getting significant differences when you compare over about 2. Now from these data, that would kind of tell you, anything over about 2 drinks, you're probably kind of in trouble in terms of being more likely to make significant more driving errors. Now, I'm not meaning to say, hey, you can have a couple drinks and drive. I'm not meaning to say that at all. That's not a good idea anyway. But in terms of statistical analysis, kind of in the plain English part, and I wrote a lot of homework feedback and said things several times saying, what does this mean? And I use the phrase plain English. I've used it here a lot too. You get past about 2 and, you get in real trouble at about 4 or so. You start getting in trouble there, so that's kind of what the data bears out. So if you were brave enough to write this up, you've got 1, 2, 3 different pairs that were significant. 1 and 6, no, sorry, 0 and 6, 1 and 6, and 2 and 6. So 6 is significantly higher than 0, 1, and 2. So you can say it that way, kind of in plain English. And you got the others are not significantly different, but they're probably different. Like this point, like I say, this point 055, that's close enough to scare me in this particular situation. So that's the homework problem. Any other questions, thoughts about that? Okay, thank you.